Okay, so in this video, we'll prove our very first graph theory result. And so in the previous video, we talked about the basic definitions, right? Vertices, edges, degree, endpoint, adjacent, incident, all these terminology that, you'll have to get used to when you talk about graphs. And we talked about degree sequences. And just as a recap here, we said that the degree sequence of a graph, that's basically this non-increasing sequence of numbers formed by, counting at each vertex how many edges are incident to it. And then writing the numbers down in non-increasing order. Right? And so we ended with the question, well, can we do the reverse? Can we start with a degree sequence and conclude whether or not there is a graph that came from that degree sequence? And I'm just going to stick with simple graphs for now in relation to that question, right? So I'll give you an example. Is there a graph with that degree sequence, right? 6 ones, right? 1, 1, 1, 1, 1, 1. And well, what are some things you know about degree sequences? There's 1 degree per vertex, right? So in this case, you have 7 numbers here because there are 7 vertices. And so in this case, with 6 ones, you know that there are going to be 6 vertices. So can you draw edges connecting these vertices so that you get 1, 1, 1, 1, 1, 1? And yeah, try figuring it out yourself if you want. Try pause the video right now and just draw something and see if you can get this. Okay, so did you get it? Well, what happens if I draw an edge like that? Well, the degree of this vertex goes up by 1. The degree of this vertex goes up by 1. And they're already at 1, so you don't need to draw any other edges connecting those first 2 vertices on the left. Let's draw an edge here. So the degree here goes up by 1. The degree here goes up by 1. And you're done, right? They both have 1s. And so on. And now this is a graph, right? That has this exact degree sequence. And maybe it's clear to you, or maybe it's not yet clear to you, that if I were to add an extra 1 here, and say, well, now I need a graph on 7 vertices, such that all the vertices have degree 1. You can try it, right? Just redo everything that we just did here. You'll quickly see that you're not going to be able to do it. Right? So I can draw something like, okay, 1, 1, 1, 1, and then 1, 1. And what's going to happen is you're always going to have something left over. The reason for this, the reason why we don't get a graph with this specific degree sequence of 7 ones is due to the next result here. And it's called the degree sum formula. In fact, you would have seen this when we were trying to draw that graph with degree sequence 1, 1, 1, 1, 1, 1, right? 6 ones. Right? So remember what we were doing there. Whenever I added an edge, degrees go up by 1 for these vertices. Right? I added another edge here, they go up by 1. And notice that whenever I add an edge, the degrees of 2 vertices go up by 1. In other words, for every edge I add, right, into my graph, the total degrees, right, the total sum of all the degrees of your vertices, it's going to go up by 2 each time, right, which is an even number. But we can actually do one better than that in terms of the argument here. In fact, if I add the edge UV, right? So if my graph G has the edge UV in it, then if I add that edge to the graph, then the degree of u and the degree of v go up by 1 each. Right? So I know exactly which degrees go up. Right? It's the vertices that are exactly the endpoints of this edge that I'm adding to the graph. And then what? Then the sum of all degrees, right? So I was saying up here, goes up by 2. Okay, so see what happened there. Every time I add an edge, the sum of all degrees goes up by 2. Look at the sum here. Right? On the left, you have the total degree for all your vertices. Right? And on the right, you have exactly twice the number of edges. Right? And this is basically the argument for that. Right? The contribution of each edge to the sum on the left is exactly 2. Right? So I'll write it that way. Each edge in your graph contributes 2 to the total sum of all vertex degrees. And so V in the vertex set of G. Therefore, this sum is exactly going to be equal to, well, twice the number of edges. If m is the number of edges, then it's 2 times m. And this actually gives us an easy way to check whether that a degree sequence can't be realized as a graph, right? Because this tells us that the sum must be an even number, right? So that's going to be a corollary here, or a direct consequence of this degree sum formula. That the sum of degrees in the graph, let me write this down better here, in a graph is even. So in other words, 1, 1, 1, 1, 1, 1, 1, right? So 7 ones is not the degree sequence of any graph. Right? Simply because if I add all those degrees, I get a 7. And in fact, one other result that's a consequence of this degree sum formula is this one, right? It's not just talking about, the total sum of all the degrees. Well, if you know that the degrees all sum to an even number, what that means is, sure, you can have vertices of odd degree. It's just that there has to be an even number of them. Right? So I can do something like 2, 2, 2, 1, 1, 1, 1. And this is fine. Right? If I have a vertex with even degree, then you're good, right? It's really, it won't really do anything to violate the degree sum formula in terms of parity. But you have to look at the vertices of odd degree. If I had 5 ones here, then I'm going to get an odd number when I add everything up, right? And so this is a direct consequence. And it's called the handshake lemma here because it's a way for you to visualize why it's actually true as well, in terms of the same argument that we used in the degree sum formula. Right? They're pretty much the same result. And it's called a handshake lemma because if you think of each vertex as a person, and each person, you have like 4 people here in one place. Some of them shake hands with some of the others. So this person shakes hands with this person, and you can draw an edge between two people if they shake hands. Right? Another way to phrase this is that in a gathering of people, there must be an even number of people who shook hands with an odd number of other people, right? I mean, that sounds kind of clunky, right? But it's exactly the same statement, right? So if these 4 vertices were people, this person only shook hands with one other person, right? So they're odd. And these people shook hands with an even number of people, right? So it's basically the same. That's just saying, well, you must have an even number of vertices of odd degree. Okay, so now it's easy to check. If you have something like 4, 3, 2, 2, 1, 1, immediately say, yep, it's not a graph, right? You can't have a graph that has this specific degree sequence. Now, I should note, though, that the reverse of the statement is not necessarily true, right? It's not true that any sequence of numbers with an even number of odd degree vertices can be realized by a graph. Right? So the converse of this statement is not true. Just because you have an even number of odd degree vertices, it doesn't mean you're going to get a graph with that. Right? I'll give you a simple example. Is there a graph with degree sequence 5, 5, 5, 5? Right, so you have an even number of odd degree vertices here, right? There are 4 of them, which is an even number. Well, clearly there's not, right? Because you only have 4 vertices. And the maximum degree for each is going to be 3. Right? I guess I should have mentioned here that we are talking about simple graphs, right? So in the context of simple graphs, that doesn't necessarily guarantee that you're going to be able to get such a graph.